Okay, hello everyone. Hello everyone again. Hopefully my audio is working this time and everyone can hear me. So this is the second of two talks I'm doing today. So in the first of the three webinars, we sort of heard about the different threats to GNSS, and we heard how we've quantified that threat and what kind of threats are available in the wild. And then in my last talk, I talked about, well, what can we do to geolocate those threats, to find the threats, to decide where the jammers and spoofers are so that we can remove them and do something about them. So now we're getting really down into the crux of the problem with this last talk here, which is what can we do at the user level in your end user equipment to protect it from any jamming and spoofing and mitigate the problems despite there being jamming and spoofing and other sorts of interference out there. So that's what I'm going to try and talk about. It's going to be a bit of a whirlwind tour again, and it's going to be a little bit technical, but again, I hope there's something in this for everyone. So what are we going to cover? We're going to talk about what we mean by anti-jam. What are we actually trying to achieve with anti-jam techniques? I'm going to talk a little bit about things you can do in the receiver. So what receiver manufacturers are doing in modern GNSS receivers to protect from jamming. Then I'm going to talk mostly about antenna techniques, which is arguably the single most powerful thing you can do to protect yourself from both jamming and spoofing. And so that will cover both jamming and anti-spoofing as well. And then we'll have a bit of a summarize at the end and see what we've learned. So let's get straight into it then. We've got a bit of a busy diagram to start with. What's this telling us? So what I'm trying to say here is this is a little illustrative chart, if you like. The x-axis along the bottom is the distance between your receiver and a jammer on a log scale, going from 1 meter to 100 kilometers. And then the vertical y-axis, for the moment, we'll just call it the jammer strength. So and those sort of diagonal lines, the light blue one, the red one, the green one, and the dark blue one, those represent different jammers of different powers. So the dark blue one at the bottom is your sort of typical cigarette lighter 10 milliwatt type jammer, going up to your 1 kilowatt jammer at the top there. So those are some example jammers that you can find out in the wild. And as you get closer to the jammer strength goes up. Okay, so no surprises there. Now that horizontal line, the sort of purple one, is one that we can use to represent a GNSS receiver, and we can pick a threshold. So different receivers will have different different positions on that vertical axis, and that is the threshold at which the receiver falls over. So in this case, what you can see is the intersection between the dark blue line and that horizontal purple line is at about 200 meters or so. So what that's telling you is, for this cigarette lighter jammer, under ideal propagation conditions, would likely cause that receiver to fall over from a distance of about 200 meters. In reality, it's not as bad as that because propagation isn't ideal, but it gives you an idea of the problem in big handfuls. And then we've got that little arrow there that I've labeled with a green box, which is the amount of anti-jam we need. So in this case, what I've shown is that big jammer with the light blue line. If you want that receiver to work against that jammer at that distance, then what you need to do is try and drop that jammer strength down by whatever that is, about 45 dBs. You can see on that jammer strength axis, to get it below that receiver threshold. So that's what we're trying to do with anti-jam, is make those jammers look smaller, move those lines down so that the receiver can deal with it. Okay, so before we get carried away with technology, it's always important to remind people that there are some very simple and obvious things that you can do to protect yourself from jamming before you start resorting to big or expensive equipment. And the first thing you can do is the right-hand diagram there, which is to simply dig yourself a hole and put your GNSS receiver in that. And why do you want to do that? Well, because satellites generally come from the sky, and typically jammers will come from a low elevation, somewhere near the ground. So if you put your receiver in a hole, yeah, you can often get, about 20 dBs of protection, and you're halfway there to protecting yourself from a big jammer. And in fact, if you go back 10, 15, 20 years, that is in fact what people used to do in the army when they encountered jamming. It was a very nice way of just dealing with the problem, is to quickly dig a hole and get a position fix. The other thing, of course, you can do is to try and give yourself some distance. Distance is your biggest friend when you're trying to protect yourself from jamming. So if you happen to be an aircraft, you can inherently get, very high levels of protection, in this example, about 90 dBs of protection, just because you're at cruising altitude, which is a long way from the jammer, but also because your antenna is on the top of the aircraft and pointing at the sky and not pointing at the jammer on the ground. So doing some simple things can often give you large amounts of protection before you need to resort to technology. Okay, but assuming we can't do any of those things, we need to start thinking about how we can enhance our equipment. So here's a GNSS receiver, and there's kind of 3 bits to it that I've labeled there. There's the antenna on the left, and then you've got the radio frequency front end in green there, and then you've got the digital signal processing, which is doing all the navigation function, if you like, on the right-hand side. And we can choose to enhance sort of either of those bits, the antenna or the receiver itself, or both. And it's important to remember what we call dynamic range here, is if you want to try and enhance the receiver, you've got to make sure that it's able to cope with jamming signals, which tend to be very large. So you've got to make sure you've got enough dynamic range in your front-end components to be able to handle that jamming signal in the first place, so that you can try and get rid of it in the electronics of the receiver. So dynamic range is quite an important thing to think about. Okay, so what can we do with receivers then? Well, right in the first presentation today, John mentioned multi-frequency, multi-constellation receivers. So that's the first thing we can do. If we look at that picture there, that's showing the GPS signals at L1. And if we have a cigarette lighter jammer coming along, that will take out those signals. They tend to be about 30 megahertz wide. So that will take out the civilian signal and even the military signals on L1. If we have the luxury of a modern receiver, which is multi-frequency and multi-constellation, then we get all these other signals that we can use as well. I've just shown GPS and Galileo here, but of course there's Beidou and GLONASS and other up-and-coming constellations. And now, of course, in this case, we've used an L1 jammer, which is taking out GPS. So it's also going to take out Galileo E1 because it's on the same frequency. So as long as you've got an L1 only jammer, we can still make use of some of these other signals that are around on these sort of the L2 or the L5 frequencies. But a lot of jammers these days are becoming multi-band. Most cleverly designed GNSS jammers these days are multi-band, and this blue one I've shown on here is designed to take out all of those frequencies. So multi-frequency, multi-constellation is helpful. And it will protect you against some threats, but it certainly won't protect you against all of them. So that's always a useful thing to do, but we need to do something else as well. So the next thing that receiver manufacturers like to do is to try and filter out the jammer by getting rid of it in some way. So here's an example of the GPS CA code. And on there, we've got 2 little jammers on there, which are those spikes you can see sticking up, and they're jamming the receiver at the moment. And those are narrowband spikes, which are very typical of perhaps some unintentional interference nearby, perhaps from something that's re-radiating that shouldn't be. And of course, the simple thing to do is in the frequency domain is to try and filter those out. So you put a notch on them, and you get that orange signal by getting rid of them. And there's lots of variations on this theme. What I've shown you there is called adaptive notch filtering. You can also do frequency domain excision. You can do something called wavelet transform excision and sparse transform excision. All these different things essentially are trying to filter out the interfering signal in some way. And this is very typical of what modern GNSS receivers will try to do, at least one of these techniques to get rid of those signals. And of course, there is a problem with that. You can see that orange signal has been degraded a little bit because inherently by filtering out that interfering signal, we've taken out some of the wanted GNSS signal at the same time. So if we just look at that in a bit more detail, what I show here on the left is the full L1 band with all the GPS signals in there. You've got the narrowband CA code in the middle, and you've got some of the new civilian codes, the L1C there, and then you've got the light blue one, which is the military PY code, and then the black one, which is the new military M code. And if we just use one of those little cigarette lighter jammers, they typically work over 30 megahertz bandwidth. So you can see on the right-hand side that is taking out all of those signals. And trying to do a filtering technique in the receiver isn't really going to help you here, because you're just going to end up taking out all of the signals you're interested in. So you're going to degrade the GNSS signal so much trying to get rid of it that you won't be able to navigate still. So we need to think of some other things to do. So at this point, I just want to introduce a concept that we call diversity. And diversity is, what do we mean diversity? We're talking about exploiting things that are different between jamming and the real signals, the real satellite signals that you're interested in. So there's code diversity, which is how GNSS works in the first place. Every GNSS satellite is essentially a jammer to all the others. And the only reason GNSS works in the first place is that we're using different spreading codes so that we can pull those signals out of the noise and track them. So that's code diversity. Frequency diversity we've just looked at, which is exploiting different frequencies of interest. If you're being jammed on one frequency, then let's use a different frequency if we can. Time diversity is a bit more subtle, and that tends to come in when you've got complex jammers like pulse jammers, which are going on and off with time, and we can perhaps do some pulse blanking. And the last one is spatial diversity. And this is the really powerful one, and this is where we're going to get into antenna techniques. Spatial diversity is exploiting the fact that typically jammers come from different directions to the satellite signals. So we can exploit the fact that jammers arrive from different directions to the satellite signals that we want. So we can start to do spatial filtering. So let's have a look at how that works. So anti-jam antennas, this is arguably the single most powerful technique that you can use to protect yourself against jamming. And they come with lots of different names. They're sometimes called adaptive arrays, phased arrays, adaptive antennas, or controlled reception pattern antennas is also a common name in the GNSS community, or SERPAs. So what is one? Well, what it is, it's essentially, rather than having one antenna, you have a group of antennas. So in this diagram, we've got a primary antenna that's labeled P, and then what we have is a number of auxiliary antennas that we've called A1, A2, and so on up to AN. You can have as many of those as you like. And then if we look at that signal that's arriving, so that could be a satellite signal, or it could be a jamming signal that's sort of arriving from the side there. You can see that it's arrived at antenna A2 before it gets to antenna A1. And later on still, it will get to the primary antenna P. So you can see that signal will arrive at each antenna at a slightly different time. And if you look at underneath the auxiliary antennas, you can see some things called W1, W2 to WN. Those are what we call weights. And weights you can think of as just phase shifts for now, if you want to think about it in simplified terms, just a phase shift. So if we phase shift the signal from antenna A2 so that it's delayed, we can get it to line up with the signal that's arriving at the primary antenna P. So if you think about it, you can, by careful adjustment of those weights, you can cause all of the signals to line up in a particular direction and give you lots of gain in that direction. Or conversely, you could get it so that the signal cancels out in a particular direction and you don't see anything in that direction. And that's how we do anti-jam. So we're causing destructive interference in a direction of a jammer. Or conversely, we could cause extra gain, constructive interference, in the direction of the satellites that we do want to see. So here's an example of what that actually looks like as an implementation. So we're getting down into the technical details of how you implement this now. So I don't want to put people off, but there are two main approaches to this. And the first one is called space-time adaptive processing, or STAP. And this is the sort of technique that the military users will be using. Military anti-jam products will contain this kind of technology. So you can see at the top there, you've got your antennas, primary and auxiliaries, and those green bits are the RF front end. So that's just a standard RF down conversion chain with your amplifiers, filters, and mixers, and so on. And then a bit further down, we go into ADCs, that's the analog to digital converters. And then we go into the weight calculation. So what we can see there are some FIR filters. And those are what are we using to apply the weights that we talked about, the phase shifts or the time delays that line up in a particular direction or cause destructive interference in a particular direction. And that little equation on the left-hand side there, the optimum weights, that's called the Wiener-Hopf equation, which is a textbook equation in adaptive signal processing. And what that's telling you is the optimum weights that you need to apply in your filters there to give you minimum jammer power coming out at the bottom. And what we're doing there is summing all the outputs of those antennas together at the bottom and feeding that into your GNSS receiver. So all you have to do is take your existing antenna off the receiver, put this on the front of it instead of your old antenna, and that will provide an anti-jam function. And you can start doing other things that we'll talk about later. So we can do some of the things I talked about earlier. We can do direction finding and signals intelligence and that kind of stuff we can start to do now that we've got this antenna array. The second approach is called SFAP, which is space frequency adaptive processing. And this is the second technique that the military like to use. And again, it's exactly the same as the previous one. The difference is it's done in the frequency domain rather than the time domain. So after the ADCs in this case, we buffer that data and then we do FFTs to turn it into the frequency domain. And then we apply our weights in the frequency domain. and then do an inverse FFT back again, unbuffer it, and then that signal will then drive the antenna input of your GNSS receiver. There's a lot of arguments going around about whether STAP or SFAP is better. I would say they are both equally good. They're both equivalent, but it really comes down to the efficiency of the implementation. Depending on what you're implementing this on, whether it's an FPGA or an ASIC or some other kind of way, SFAP can sometimes be a bit less efficient to implement than STAP. But in broad terms, they're equivalent, and they're both very, very powerful anti-jam techniques used by the military. So let's just take a look at what that means, because that was a bit theoretical there. So there's two pictures here. These are antenna patterns. So the one at the top right is an example of a jammer. A single jammer is appearing from the red direction. So that red line is the direction of arrival of a jamming signal. And in this case, we've got a low elevation satellite, which is the blue line coming from the back there. And so what you can see is that adaptive antenna, that anti-jam antenna, is steering a null in the direction of that jammer. And as that jammer moves around, the antenna pattern automatically adapts and tracks that jammer so that you've never got any antenna gain in that direction. And so it's filtered it out based on the direction of arrival. And the diagram at the bottom there is showing the same thing, but with two jammers. So we've got two red lines showing direction of arrival of two different jammers. And you can see it sort of punches a hole in the antenna pattern around both of those. So it's quite possible that occasionally you will lose one satellite or two if they happen to be coming from a similar direction to the jammers. But most of the time, you've still got a good number of satellites that you can see. So that's null steering. And the last thing on this is something we'll call digital beamforming, and this is one further step that you can take, and it's kind of the ultimate solution in terms of performance. And so what we've got here is the space-time adaptive processing that you saw in the first example with those FIR filters there and your weight calculations. But what we're doing is, instead of minimizing the jammer power, we're still minimizing the jammer power, but we're also trying to maximize the satellite power at the same time. And to do that, we need to steer a beam towards each satellite. And because we've got lots of satellites, we need one beamformer for each satellite that we're interested in, which is why we've got lots of the sort of purple boxes there, one of those for each satellite, and we're using that to steer a beam towards each one of those. And that gives you a sort of 10 log n further gain improvement, where n is the number of antennas you've got there. So if you've got lots of antennas, you can get a very, very powerful anti-jam technique from doing this. And because we've now got separate outputs at the bottom there, you can see there's 4 different outputs there representing 4 beams. So typically with a beamforming solution like this, we need to feed that directly into the tracking loops of a GNSS receiver rather than through the antenna input. So digital beamforming does have some more interfacing concerns. What does beamforming look like? Well, it looks something like this. So again, we've got our jammer, in this case, is that red line. So we're still nulling out that jammer in a very powerful way. But we've also, where that blue line is, that's the direction of arrival of a satellite. So we're steering lots of antenna gain in that direction. And that's a really, really powerful technique that's been used for many years by the military and is becoming more available again to critical infrastructure. So it's worth just having a little look now at what do these pieces of hardware actually look like. So here's a bunch of military anti-jam products from different years, starting off on the top left there from 1984. That's, as far as I'm aware, the world's first GNSS anti-jam product. We developed that here in 1984, and it was trialed by the US at the Yuma Proving Ground, and that could defeat 3 jammers simultaneously. It was using analog electronics. And those sort of early products informed something called the GAS-1, you can see at the bottom left, which is a Raytheon product. And that was around about 1997 that came out. And that became the de facto standard anti-jam technology, which is still deployed today on fast jets, on the Typhoon and the F-35 and all these kind of platforms. It's kind of got replaced around 2005 with something called the ADAP, which looks very similar, but it's using digital techniques. At the bottom in the middle there is something we did back in 2013, which is a special type of conical antenna, which has been used specifically to protect timing receivers in this case, rather than navigation receivers. And that was deployed on military land vehicles. The one on the top right there is an example of a conformal curved antenna, which was for anti-jam to apply to a missile. And then on the bottom right there, we've got some Raytheon products, which are designed to fit on land vehicles. So they come in all shapes and sizes for fitting onto all sorts of different platforms, and they are very, very powerful techniques indeed. So that's anti-jam. Let's just talk briefly about anti-spoofing. Most anti-jam antennas that we've just been talking about do not protect you against spoofing. They only protect against jamming. And why is that? That's because they're trying to get rid of jamming signals. They're looking for signals that shouldn't be there above the noise floor and getting rid of those. Spoofing is often below noise, as we've heard, so it can't be defeated in the traditional way. However, some anti-jam antennas will protect you against spoofing. The picture I've shown you here is an experiment we did here to spoof a GNSS receiver, and we actually protected it with an anti-jam antenna. And this is just to illustrate the point that anti-jam antennas don't necessarily protect you against spoofing. So this was a stationary receiver, and we spoofed it off into the woods, writing the word roke as it goes. However, some GNSS anti-jam antennas can protect you against spoofing, such as the Landshield Raytheon product is an example of that I've just shown you. And how can they protect against spoofing? Well, they do that because they've got those correlators in there that we heard about earlier when we were talking about geolocating spoofers. These anti-jam antennas that can do anti-spoofing have those correlators in there so that they can track the spoof signals and defeat them then with nulling. So here's an example of anti-spoofing on an anti-jam antenna. So this is just an example of something that the user interface can show you. So if you're familiar with looking at GPS receivers, you'll be familiar with some of this. So we've got a load of lines there which are tracking channels. Each one of those tracking channels represents a satellite or a spoof satellite in this case. And so it's tracking every satellite it can find, including every spoof satellite it can find. And then what's it doing? It's looking at the direction of arrival of those spoof signals. And if it sees a lot of signals that are coming from either a similar direction or a direction that they shouldn't be coming from, then it can declare that to be a spoofing attack. So you can see at the top there, it's detected a spoofer. And then at the top right, you can see it's actually done some direction finding on that spoofer, and it gives you the azimuth and the elevation of it, telling you where that spoofer is, and a degree of confidence. It's 94% confident as to where that spoofer is. And we can then start to locate it and classify it and all those kind of things as well. So the other thing that you can do with anti-jam antennas now, certainly the modern ones, the latest generation of anti-jam antennas, we've talked about doing anti-jam, which has been around for decades now. Anti-spoof has come along in the last 4 or 5 years. And they're now starting to take on much more of the signals intelligence side of things and situational awareness. So what we're showing here on the left is a time domain plot of 3 different jammers in an environment. So the top one there is just a sine wave, so that's a CW jammer. The middle one on the left is a broadband noise jammer. And then on the bottom there, you've got a chirp jammer. So that's your sort of personal privacy devices, your cigarette lighter jammer. And when those all mix together, the middle diagram there is what a GNSS receiver sees. And that receiver is well and truly jammed. It's not going to operate. In the adaptive antenna that we've just been looking at, we can separate those out again because we've got those multiple antenna elements with spatial degrees of freedom. We can separate those out. So we can actually, in the antenna itself, unmix those signals and separate them out again into those 3 components. And why do we want to do that? Well, we want to do that because we want to know what sort of jammers are out there. We want to know how many jammers there are, and we want to be able to classify them. So Mark talked a little bit earlier about classification. So we can identify individual jammers. And so I'm just going to finish off on that point, just to talk a little bit about interference classification. Is that once you've separated those signals, you can classify them. So this is an example of 8 different classes of jammer. So continuous wave, noise jammers, chirp jammers, BPSK, Bok jammers, and a couple of others. And the diagram on the left there, that bar chart, is showing the true class of those jammers against the probability of classifying it. So you can see we're at about 90% classification accuracy. And another way of viewing that is the diagram on the right, which is called a confusion matrix, which is sort of plotting the true class along the bottom against the predicted class up the side. So that's showing that we can very accurately pick out individual jammers from multiple jammers all jamming at the same time. We can pick those out, we can direction find on them, we can classify them, and we can defeat them so that the GNSS receiver never has to deal with them in the first place. So just finishing off on a Raytheon picture here, this is a bit of a marketing slide, but it kind of gives you an idea of the state of the art now. Is we've got some vehicles here that fitted with anti-jam antennas. And so those are protected from any jamming in the vicinity. But what they're also doing is situational awareness. So they're doing direction finding on the jammer and geolocating it, and they're classifying it, and they're simultaneously looking for spoof signals and classifying and detecting and geolocating spoof signals. So that's the kind of thing that's going on in the latest generation of anti-jam and anti-spoof technology. Okay, the last thing I'm going to talk about is a question I get asked quite a lot, which is, can I have one of these anti-jam antennas? You know, are they export controlled? Are they classified? So here's the answer. So yes, anti-jam antennas are export controlled. So in the UK, they sit on something called the dual use list, which means they're essentially for military use, but also for civilian use as well. So they are export controlled. They sit on the dual use list under export control item 7A005, which is global navigation satellite systems receiving equipment employing adaptive antenna systems. And all that means is you need an export license to export those from the UK. At the moment, they still sit on the open general export license, which means they're very, very easy to export to most, I guess, sensible countries. And in fact, I've exported them to 42 different countries without any problems whatsoever. So they're relatively easy to export. If you get one from Canada, they're subject to the Controlled Goods Program of Canada. And if you try to get one from the US, you'll likely have lots of problems because they attract ITAR and nasty things like that. So in the UK, they're nice and easy to get hold of. From the US, they're less easy to get hold of. So that's it. We've covered quite a lot again in a very short period of time. So I hope there was something in that for everyone. So I'll just summarize what we've talked about. So I started off talking about the aim of anti-jam. I showed you that graph showing distance from the jammer and what level of anti-jam we need to defeat different jammers at different distances. And then we talked about the quick and easy wins, as I like to call them. It's what can we do before resorting to technology? We can dig a hole. We can try and mask off those low elevation jammers. We can increase our distance to the jammer. We might be able to put our receiver in the air and create some distance between us. Those are the quick and easy things that we can do. Then we talked a bit about receiver techniques, what GNSS receiver manufacturers are doing these days, looking at multi-frequency. We talked about excision methods for removing some narrowband jammers. What we didn't talk about is aiding, and that's bringing in other sensors to help aid the GNSS. And Terry Moore, I believe, will be talking about that in the next webinar next week. And then I moved on to antenna techniques, which are the really powerful ones that we can use. And we looked at adaptive nulling for removing jammers based on direction of arrival. We talked about adaptive beamforming, which takes that a step further by steering extra gain towards the satellites themselves. And we looked at two different ways of doing that using space-time adaptive processing and space frequency adaptive processing. And then I showed you some examples of anti-jam antennas, some typical military products. And we looked at anti-spoofing. And we talked about situational awareness right at the end there, about how we can not just defeat the jammers, but we can geolocate them and we can do classification of them as well. And then right at the end, we've just looked at briefly at export considerations. So I guess the situation is, at the moment, it's mainly the military that are using these things and have been for decades, but they are available to critical infrastructure and other users as well. It's just at the moment, most people choose not to use them for various reasons, either because they think they're not available to them or because they're too big, too power hungry for their particular application. Okay, I'm going to leave it there because I've talked quite a lot. I'm Michael Jones and I'll hand you back to Claire now. Thanks very much for listening.